This lecture will conclude Chapter 3, and it teaches you how to write and interpret electron configurations. Electron configurations are like an address that describe the location and energy of every electron around the nucleus of every atom. And it's in the format that is shown right here, which I would think you've probably seen before, where in general it's a combination of a number followed by a letter and then an exponent, where the number represents the quantum number n, the energy level, can be 1, 2, 3, etc., moves up in integers. The letter, in this case S, is the sublevel. That's the L, angular momentum quantum number, tells us the sublevel within the energy level. And the exponent in electron configuration represents the number of electrons that are in that particular sublevel. Now, you have to be able to differentiate between electron configuration that we just went over, like this, and an orbital configuration or orbital diagram. If you're asked to draw an orbital diagram, it's looking for boxes and arrows, okay, where the box represents an orbital. There's a separate box for every orbital, and the arrows represent the electrons. Now, before we get going, writing electron configurations, there are some kind of guidelines and rules that you need to be aware of. And since the electron configuration is in the format of starts like this, they all start like this, okay? It's important to know the maximum number of electrons that each sublevel can hold. So anytime you're dealing with an S sublevel, the maximum electrons it can hold are 2. So anytime you get to draw an orbital diagram, for example, for an S orbital, there will only be one box, and then assuming the exponent is 2, you'll put in 2 electrons. A P sublevel has 3 orbitals. So let's say we had 2p6 was part of the electron configuration. Every time you draw an orbital diagram and there is a P sublevel, there are 3 orbitals, so you have to draw 3 boxes, one for each orbital, and then put however many electrons in those orbitals as the exponent tells you to. A D sublevel has 5 orbitals. It means 5 boxes if you're drawing an orbital diagram, and an F sublevel has 7 orbitals. So this you just need to commit to memory. So the rules, there are 3 rules that you have to be familiar with, and one is the Aufbau principle. It very simply says that electrons enter the lowest energy available orbital. So I'm going to draw a Bohr model of an atom. So let's see, there's n equals 1, n equals 2. And if you are placing electrons, electrons will go into the first energy level first until that first energy level is filled up before they enter the second energy level. That is the Aufbau principle. Another rule is called the Pauli exclusion principle. And a very oversimplified way of stating that, but it's easy to understand, is that if an orbital has 2 electrons, they must have opposite spin. So every orbital, I'm not talking about sublevels, I'm talking about an individual orbital, can hold a maximum of 2 electrons. And if it does hold that maximum, they must have opposite spin. That's to minimize electron-electron repulsion, by the way. You can have an orbital that's not totally filled with 1 electron, okay? So now, the official Pauli exclusion definition and what you're likely to see on an end-of-course standardized test is that no 2 electrons in an atom can have the same 4 quantum numbers, okay? So let's imagine we have a 1s orbital with 2 electrons in it. The Pauli exclusion principle says that these 2 electrons must have a unique set of 4 quantum numbers. So I'm just going to show you the quantum numbers for each of these 2 electrons. They are both in energy level 1, so n equals 1 for both of these electrons. They're both in an s orbital, so L equals 0 for both of these. Anytime L equals 0, m sub L must also equal 0. However, since one is spin up, the convention is to assign the ms value of plus 1/2 if it's spin up, and the other electron has an m sub s quantum number of minus 1/2. So you see that both of these electrons have a unique set of quantum numbers. And also, hopefully, you see my very simple definition of if an orbital has 2 electrons, they have to have opposite spin, because it is, in fact, the spin that makes 2 electrons in the same orbital have different quantum numbers. Okay, the third and last rule is if you are placing electrons into a sublevel with more than one orbital, so for example, a p sublevel, each of the 3 orbitals in a p sublevel have equal energy. But to minimize electron-electron repulsion, if you're dealing with multiple orbitals that are at the same energy, you put 1 electron into each of them before you pair them. So you would never do something like, see, this has a total of 4 electrons in it, the p sublevel. You would never do this, okay? Put 1 electron in each of the equal energy orbitals before you pair any. That's Hund's rule. All right, so those are the 3 rules. This slide is just stuck in to kind of prompt you to start thinking about periodic trends, which is our next PowerPoint, and a really important facet of understanding periodic trends is understanding effective nuclear charge. So the nucleus itself is positively charged, right, because it has protons in it. And so clearly the electrons outside the nucleus are very attracted to the nucleus, okay? Now, the more protons you have in the nucleus, the stronger the attraction is. But sometimes that level of attraction is reduced by electrons that lie in between the nucleus and the electron in question. In fact, for every energy shell that you fill up with electrons, outer electrons are going to feel less and less effect from the nucleus. Another oversimplified way of saying that is the farther an electron is from the nucleus, the attraction goes way down, not only because of distance, but because of all of the, we call them inner core electrons, that are effectively shielding the nucleus from the outer ones. So that's effective nuclear charge. So you may have a nucleus with 10 protons, and if you have multiple energy levels, the electron out here is not going to feel the full attraction of those 10 protons because it's going to have electrons in the inner closer levels that are going to shield it from feeling the full effect of the nucleus. So the Aufbau principle, if you remember, says that electrons go into the lowest energy level orbitals first, and here are the energy arrangement by energy of orbitals. So when you're writing electron configuration, you pretty much have to commit to order the energy, the relative energies of them. And it may seem overwhelming now, but it's pretty easy. If you want to write it out longhand, this is the ordering that you write electron configuration. Whoop, I need to do that. Electron configurations in. so I got you started. There are some anomalies, and the first one I want to mention to you is that s orbitals and the higher energy levels actually end up, once you put electrons into them, actually end up being lower in energy than the previous d sublevel. So that's true starting with 4s, and then when you get to 5s, 5s comes before 4d, 6s comes before 5d, and etc. So that's just kind of a little quirk you need to remember. This isn't called an Aufbau diagram. So it's easy to write electron configurations for elements that have kind of the lower atomic numbers, but when you get up to the heavy metals or toward the bottom of the periodic table with a lot of electrons, it can get pretty confusing to know the ordering of the sublevels to start with. So here again is it longhand if you want to jot that down. This Aufbau diagram is kind of cool. You can create it on your own, like let's say if you're on a test and you freak out and need help. So you line up all the S sublevels, then you leave a space and you line up all the P, then leave another space, line up all the D, leave another space in F, okay? So once you do that, you follow a diagonal pathway from the top. So this tells you 1s orbital comes first, and we can see that it does. Then you loop, go back up to the hind end of each arrow. So that tells us 2s comes next, and we see it does. So loop up again until you get to the hind end of the next arrow. Now it gets more interesting. Okay, then we hit 2p and then 3s. Loop back up, 3p and 4s, etc. So if that's handy to you, it's there. If not, you can fit it. Alrighty. So we already went over the 3 rules. I'm not going to drill them in again, but there they are if you want to print them out or jot them down. All right, so here are the electron configurations and orbital diagrams for the first several elements. So what you have to do, you have to have a periodic table handy, and if it's asking you for electron configuration element, find the element on the periodic table and look for how many electrons it has. So we assume that all of the elements on the periodic table are neutral, okay, unless we're told otherwise. So what that means then is that the number of electrons in a neutral atom equals the number of protons. So just look for the atomic number on the periodic table, and that tells you not only the number of protons, but it also tells you in a neutral atom the number of electrons. We see then hydrogen has 1 electron, so we put that 1 electron in the lowest energy level, which is 1s, and we write the electron configuration as 1s1. Helium has atomic number 2, which means in its neutral state it has 2 electrons, so that would be 1s2. Once you get to 3 electrons, you've filled up the s orbital, and you have to move to the next highest energy level, which is the 2s. Okay, so look at these, make sure they make sense to you. So I want to do ones that are a little bit trickier. So what if I asked you to write an electron configuration for iron? So you find that it's one of the transition metals, and it has 26 electrons. So you would start and you keep track of the count of the exponents you have to know how many electrons you've placed. So that's 2 electrons. That makes 4 electrons. Now we have added a total of 10, 12, 18, 20, 26, and then we stop. Okay, so that is the electron configuration of iron. And if you were asked to write an electron configuration and an orbital diagram, here's the orbital diagram. So that's something you definitely need to be able to do. Now, this is a really important part to understanding electron configurations and the ordering of elements in our periodic table. It's really kind of amazing. But on the periodic table, we call the first two groups the S block. The transition metals we call the D block. So you need to be able to label a periodic table if you're asked to, according to the blocks. The non-metal, or the right-hand side of the periodic table, is the P block. And the very bottom is F block. How did we get that, and what am I talking about? Well, if you were to write out the electron configuration of each element in the periodic table, I'm going to make it bigger. So here is the electron configuration at the bottom. See that for all of them? Now, it's just the highest energy level of each electron configuration that's shown. So the full electron configuration for lithium, for example, is 1s2, 2s1. But just to make this point, I'm showing only the highest energy level. So each of these shows the highest part, or the end part, of an electron configuration. So what pattern do you see going down any group? All of the elements in a group end with the same electron configuration notation, okay? So elements in a group, in the same vertical group, elements in a group, end with the same electron configuration notation. So in group 1A, all of them, the electron configuration all end in S1. So really, this is called the S1 group. Group 2, they all end in S2. The S2 group. See, no surprise. And then you see, as you go, the transition metals, D1, D2, D3, D4, etc. Oh yeah, don't worry about those being off a little. We'll talk about that later. Okay, P block, again, P1, P2, 3, 4, 5, 6. So that's kind of cool. So now, you don't even really, if you understand the correlation between the periodic table and electron configuration, you don't need to memorize the ordering of orbitals for electron configuration. You should, at some point, if you practice enough, just be able to have a periodic table in front of you and spout out electron configurations. There are a handful of electron configurations that are unexpected, and you just simply have to memorize them. Chromium, the chromium group. So if you look in your periodic table, chromium's on the transition metals, and the metals beneath it, and then copper and the elements beneath it in the periodic table. They're both transition metals. So if you were to go by the number of electrons each of these elements have, and you wrote out the expected electron configuration. Now, we haven't talked about what we call the noble gas condensed configuration, but that's fine. Don't pay attention to those. I just want you to look at how you would expect the electron configuration of these transition metals to end. You would expect them, the chromium group, to end in 4s2, 3d4, but how they really go is 4s1, 3d5. So you have the same number of electrons in this higher energy level orbitals. See, they both have 6 electrons. Whoops. But what happened here? As you can see, one of the S electrons moved up to the D sublevel. And that's what happens in the copper too. So the rule here is that 1/2 full and completely full sublevels are very stable. So you can see if we look at the expected electron configuration for chromium, 4s2 is a full orbital, so that's stable, that's good. But then you have 3d4, okay? So remember in a d sublevel there are 5 orbitals. Every d sublevel has 5 orbitals. And if only 4 electrons are in that sublevel, it would look like this. Okay, so it's neither half full nor is it totally full. So that's not particularly stable. Now let's look at the actual electron configuration of chromium that has been found experimentally. So we have 4s1, so that we know that's half full, so that's good. Let's look at the d sublevel again. So let's draw out the 5 orbitals that we know are in d. And now we have 5 electrons in them. So what has happened here? That is half full. A 3d5 is a half full d sublevel. A d sublevel, when completely full, holds 10 electrons. So 5 is half full. So by promoting one of the s electrons to the d sublevel, it has made itself more stable. All right, shorthand electron configuration. As you can imagine, when you get to the large elements in the periodic table, it gets extremely tedious writing out all of the orbital configurations. So we have something called a noble gas electron configuration or shorthand configuration, where the only thing you spell out and show in detail are electrons in the highest energy sublevel. And all of the other electrons that are not in the highest energy level are represented by the nearest noble gas before that element, put in brackets. So let's look at what I'm talking about. If you were to write out the electron configuration for sodium, it would be like this: 1s2, 2s2, 2p6, 3s1. To write the shorthand electron configuration for sodium, you would look at a periodic table, identify the noble gas, that's group 8A on the far right, the nearest noble gas before sodium on the periodic table, and that happens to be neon. So the electron configuration for neon is what's in brackets there. Okay? That's the electron configuration for neon. So basically, by putting neon in brackets, we've accounted for all these electrons. And then the only thing that we have to write out is, again, the electrons in the highest energy level. So let's look at some of them. We just went over sodium. Okay. So as we move our way through the periodic table and keep adding electrons, you can see what happens. Now, you'll find that after argon, that the nearest noble gas won't be neon anymore. So we'll do a couple for practice. So any of the elements in period 3 in their shorthand electron configuration will use neon. Once you get to energy level 4, though, the noble gas you would use at that point would be argon. So again, you go back to whatever noble gas is closest before the elements that you're writing a configuration for. I want to show you here how to use a periodic table to easily come up with the electron configuration in shorthand form. All right, so let's do chlorine. All right, so what you do, you backtrack from chlorine and find the nearest noble gas before chlorine. So that would be neon. Put it in the brackets, right? Now, go to the very next element after the noble gas. So neon has an atomic number 10. We're going to go to sodium. What is the ending electron configuration notation for sodium? It's 3s. So anything after the noble gas you've got to write out. So I'm going to put 3s. So sodium is 3s1, magnesium is 3s2. So we have filled up the 3s sublevel. When we get to aluminum, we are now at the P block, right? So aluminum ends in 3p1, so now I'm at 3p, and I count all the way till I get to the element I'm interested in, which is chlorine. So I have 3p1, p2, p3, p4, and p5. Chlorine is p5. So this is the shorthand electron configuration for chlorine. Here are a couple more practice. So what I would suggest that you do is get a periodic table in front of you and see if you can in fact draw out the shorthand electron configuration for each of these, and then check yourself. Alrighty, we're getting close to being done. So we have talked about electron configurations, and especially when we get into chemical reactions, we'll be talking about valence electrons. Those are the electrons in the highest principal energy level. So, for example, if I had electron configuration 1s2, 2s2, 2 is the highest principal energy level, and the second energy level in this atom has 2 electrons. So we would say this has 2 valence electrons. Let's look at another one. Let's say we were looking at an atom with the electron configuration of this, which is fluorine, I think. So how many valence electrons does it have? Well, what's the highest principal energy level? It's 2. Be careful, because you have to count all electrons in that highest energy level. So this is 2 plus 5, okay, because you have 2s and 2p. So there are 7 valence electrons in this one. Any electrons in lower energy shells, so in this case the electrons in the 1 energy level, are called core electrons. And valence electrons are extremely important. Those are the electrons that make chemical bonds and determine chemical reactivity. What's pretty cool is the number of valence electrons an atom has matches up with its group number. If you're numbering in the 1A-B method, then all of the elements in group 1A, so there'd be hydrogen, lithium, sodium, have 1 valence electron. Okay, one electron in the highest energy shell. The elements in group 2A have 2 valence electrons, and on up 3, 4, 5, 6, 7, 8 valence electrons. Remember, we have said this before, the elements that are in the same group, the same vertical family, have similar properties. So now we know that elements in the same group not only have similar properties, but they also have the same number of valence electrons, and those two trends are related. I told you the number of valence electrons determines chemical reactivity. So all of the elements that have the same number of valence electrons are going to have similar properties. All right, so now because elements that are in the same group have the same number of valence electrons, so I'm just going to put those up here. 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons. It turns out that when neutral atoms undergo a chemical reaction, sometimes they become ions. Sometimes they either gain or lose electrons during the chemical reaction. And it turns out that atoms that have less than 4 valence electrons tend to lose electrons to become ions, and atoms that have more than 4 valence electrons tend to gain electrons when they become ions. Now, you may remember learning in high school that all elements, all atoms, like to have a full outer shell. A full outer shell contains 8 electrons. So basically, every atom on that periodic table would like to have 8 valence electrons. How do they achieve that? Well, if they only have a few valence electrons, it takes less energy for them to lose the ones they have, and then the shell underneath is full and it's stable. If an atom has a lot of valence electrons and they're close to already having 8, they will more easily gain a couple of electrons to achieve a total of 8. So now let's look. There are common charges. Elements, again, I'm going to say in their natural state are typically neutral. However, when they undergo chemical reactions in combination with other elements, they are often in ionic form. So the bottom line is when the elements in group 1A become an ion, they all have a charge of +1. When elements in group 2A become an ion, they have a charge of +2. In group 3A, they have a charge of +3. Now, where are these charges coming from? So elements in group 1 have 1 valence electron, right? They're going to lose that 1 valence electron to have a full undershell. When you lose an electron, what charge are you ended up with? Electrons have a negative charge, so when you give a negative charge away, what are you left with? You're left with a positive charge. All right, so group 4A, that's carbon on down, have 4 valence electrons. So they could either lose those 4 to have a full undershell, or they could gain 4 more to complete that top shell with 8 valence electrons. But because it's quite a bit of work, they don't tend to become ions. But if they do, they can go either way. So they can end up with a plus or minus 4. Now we're at the point where we have a lot of valence electrons, more than 4, that these atoms are going to gain electrons if they become ions. So group 5A with 5 valence electrons, 5 valence electrons, is going to gain 3 more electrons, which gives it a total of 8 valence electrons, which is very stable. It's a full outer shell. So the common charge in the nitrogen group is -3. The common charge in the oxygen group is -2. The halogens, fluoride group, is -1. And the noble gases do not tend to become ions. They already have 8 valence electrons, which is a full outer shell. They're very stable. They're non-reactive. So you need to be able to draw out the electron configuration for ions also. So we have 2 types of ion. An ion is just a charged particle. We have positively charged ions, which are called cations, and we have negatively charged ions, which are called anions. The nonmetals to the right side of the periodic table, as I said, will tend to gain electrons and become anions. The metals to the left side of the periodic table will tend to lose their electrons to become cations. So sulfur as a neutral atom has this electron configuration. My pen's not working anymore. I bet the batteries went. Maybe I'll use my finger. So here is the neutral electron configuration for neutral sulfur. Sulfur is in the oxygen group. It's in group 6A. So if you look on the periodic table, and you should probably go ahead and label your periodic now with the number of valence electrons and the common ion charges. So group 6A with oxygen, my pen doesn't want to work, and sulfur, they have 6 valence electrons, so they want to gain 2 more valence electrons to get a full outer shell. And when they gain 2 valence electrons, they get a negative charge. So oxygen as a common ion has a -2 charge pen still isn't working. I don't know what's going on here. Okay. And same thing with sulfur. All the atoms in that group, when they become ions, get a -2 charge. So when we add, so to draw out the electron configuration for the common ion of sulfur, you have to add 2 more electrons. So instead of 3p4, the sulfur anion would be 3p6. You're going to notice that electron configurations for almost all ions will have 8 valence electrons. That's the driving force for them, is they gain or lose electrons to have a full outer shell. All right, so sodium's in group 1A has 1 valence electron, and it's going to lose that 1 valence electron when it becomes an ion, so that the ion has a charge of +1. Fluorine is in group 7A, so it has 7 valence electrons. It is going to gain 1 electron to get a full outer shell, so the fluoride ion is going to have a negative charge. So just make sure however many electrons you've lost or gained that you would count for that in the electron configuration. So see here, fluorine has gained an electron, so it goes from 2p5 to 2p6. And sodium loses its 1 valence electron, so it becomes isoelectronic with neon. Isoelectronic means same number of electrons. I have seen that show up on the ACS final exam, that vocabulary word. Isoelectronic is same number of electrons. Okay, so transition metals, okay, the D block, elements in the middle of the periodic table, are odd. They do not have common ion charges like the A group do. They have various charges. So iron, for example, when it becomes an ion, can be +2, can be +3. It actually has some other charges. You'll see +2 and +3 most often. And most of the transition metals have multiple charges they can have. So we really need more information to know what type of ion we're dealing with when we have transition metals involved in a chemical reaction. But the one thing I want to point out here is look at the electron configuration for neutral nickel. So what if I told you to write out the electron configuration for nickel +2 ion? You might think, hold on, if you were to, let me back up for a sec. If you were to write out the electron configuration for nickel, most people write it like this. So remember the 4s sublevel is lower in energy than the 3d, so most of them are written like this. I've inverted them on the order on this page because when you remove electrons, you remove them from the 4s sublevel before you touch the 3d level. Okay, that's true for all transition metals. Okay, all metals tend to lose electrons and become cations, and the transition metals lose the electrons first from the s sublevel. That's an important little nuance that could make the difference between an A and B on the next test. And that is it for electron configurations. So make sure that you print out the electron configuration worksheets in D2L and get a lot of practice on this.